What's up, guys? It's Dan from SageMathTutoring.com, and here I have a few problems that are on a review sheet for a student of mine. Some of it looks like he already worked on. I'm not exactly sure whether or not his answers are correct, but we're going to go over each of these sort of problems one by one, and I'm going to think out loud about them, and hopefully that should shed light on how to solve these problems. So anyway, let's look at the first problem. So we have integer section. Simplify each expression and write your answer in the spaces provided. Work may be necessary but is not required. So what do we have here? We've got 17 minus 9 plus 6. Well, this is definitely a PEMDAS scenario where you can definitely do 17 minus 9 first, and that would, of course, give us 8. And after we get 8, we can add 6, and that will give us 14. So it looks like that is indeed correct. I'm not really sure. Well, yeah, I could see. So what my student did is 17 plus 6 first, and then subtracted 9 next. That's totally fine since addition is commutative. All right, moving on, we've got 6 minus positive 11. Yes, the negative and the positive next to each other results in a subtraction scenario. So my student correctly did 6 minus 11. In that case, it equals negative 5, so that is correct as well. Looking at the next one, I do believe this is 2 plus 8. If I'm not mistaken, that is a minus. 4 minus 7. 2 plus 8 is indeed 10. 4 minus 7 is indeed negative 3. And 10 minus a negative 3 is the same as 10 plus 3, which is 13. So my student did that correctly as well. Negative 2 times negative 1 is a positive 2. 5 times 0 times negative 9. The presence of the 0 just turns everything into 0. So that would be a positive 2 minus a 0, which will indeed give you a positive 2. Looking here, my student distributed the negative 4 into the parentheses, and that's not wrong, but I would suggest using PEMDAS, which would suggest simplifying whatever is inside the parentheses first. So therefore, it would be negative 3 minus 3. That would be a negative 6. Negative 6 times that negative 4 should definitely give you a positive 24. So my student got the correct answer there, which is good. 12 minus 0 is just 12, and then we have the 12 minus 9. Minus 1. So 12 minus 9 is 3, minus 1 is 2, so that is correct as well. Using PEMDAS, we're going to want to multiply these before we add or subtract these two terms. So let's multiply these two numbers first. We've got negative 2 times negative 3, that is a positive 6 minus 5, and that would definitely be a 1. So it looks like my student rocked this section. Good job, my friend. Moving on to the next section. All right, this one's a little blurry, so I apologize for that, but I'll read it for you in case you can't see it. An engineer is creating congruent pentagonal widgets. The expressions of their sides are provided in the picture below. All right, so we have congruent widgets, meaning that they are the same size. Write an expression for the perimeter of widget A. Show all work and write your final expression in simplified form. So let's look at widget A. Here's widget B. Here's widget A. We want the perimeter. Now, as many of you who are watching this know, the perimeter is going to be a matter of adding this side plus this side plus this side plus this side plus this side. So we could definitely write an expression representing the perimeter by saying the following. We could write, I'll start at the top, we could write x plus x plus 1 plus 2x plus 1 plus x plus 3 plus x plus 2. And at that point, what I would do is just underline all the moments where we have a term that has x in it, just to help with the simplification process. Now we're going to combine like terms. Let's in fact focus on the terms that feature x. We've got x plus x, which is 2x, plus another 2x, which is 4x, plus another x, which is 5x, plus another x, which is 6x. So we could write that. That would be 6x. And then the Terms that do not have an underline underneath it are the constants. So we have 1 plus another 1, which is 2, plus 3, which is 5, plus 2, which is 7. So we could write that, and that is definitely the answer. It looks like my student got that, so well done. Create and solve an equation to determine the value of x for widget B. If the perimeter of widget B equals 31 inches. Okay, so already I'm saying that the teacher is emphasizing an understanding of vocabulary such that the teacher wants my student to understand the difference between an expression, which is why I see this underlining of this word, and an equation. It's important to recognize that an expression is a little bit different than an equation. An expression like this does not have an equal sign in it. Notice how we ended up with 6x plus 7 and there was no equal sign. That's an expression. An equation is always going to have an equal sign. So we need to sort of be careful about that. That's a mental note that's worth making. Create and solve an equation to determine the value of x for widget B if the perimeter of widget B is 31. All right, so they're giving us the perimeter for widget B, which will enable us to solve the equation. So the first thing I would do with widget B is write down the expression on the left-hand side of the equal sign of all of this added together and set that equal to 31. So I'm going to do that right now. So let's see, I'm going to do something similar. So we've got x minus 3 plus x minus 2 plus x plus 2 plus 2x minus 7 plus x minus 1. And this time we're going to set it equal to 31 because according to this problem, that is indeed the perimeter. I'm then going to underline all the terms that have an x in it just for the sake of avoiding careless mistakes. And looking here, we've got x plus x is 2x plus another x is 3x plus 2x is 5x plus x is 6x. So we have 6x over here, and adding all the constants or combining the constant terms would be negative 3 minus 2 is negative 5 plus 2 is negative 3 minus 7 is negative 10 minus 1 is negative 11. So that would be 6x minus 11 equals 31. Now to solve this, we would have to add 11 to both sides, and we'd end up with 6x. That's a little sloppy looking. We would end up with 6x equals, what is that, 42? And then we'd have to divide both sides by 6. That cancels that. And that would result in x equals 7. And looking at this part, using an expression determine the side lengths of IH show all work. So IH is, let's see, right here. So IH is 2x minus 7, right? So we could even say that. We'd be like IH, we'll use an arrow, is 2x minus 7. Now we already figured out what x was from before. We know that x equals 7. So, of course, what that means is we can substitute 7 in for x and take it from there. So 2 times 7 is 14, and that will be 14 minus 7, which is 7. And this is another example where it looks like my student did quite well. So good job. Okay, looking at this next part, obviously there's a lot of writing here. There's a graph here. So what I'm going to do is just sort of think out loud about this information. Hopefully that will shed light on what's going on here, just in case you at home or my student doesn't quite know what's going on. I don't want to assume necessarily that my student, just because he wrote this stuff in the review sheet, that means that he necessarily knows what it means, because there's always the off chance that the teacher just wrote a whole bunch of stuff on the whiteboard and the student just kind of blindly copied it. So it's important that we understand what is even happening here. So first of all, let's analyze this graph. Money is on the left, time is on the bottom. It's often the case that when you have graphs depicting the passage of time and some other variable, that the passage of time will be represented on the x-axis. That's very common. And let's look at the first problem right now. Write the coordinates of the y-intercept and explain what it means. 1970, 3 and 0, 1. I don't know about the 0, 1 thing. Not really sure where that is coming from, so let me get rid of that. But I like this 1970, 3 thing because definitely the y-intercept is the place where the line cuts through the y-axis. Here's the y-axis. Clearly the line is cutting through in this moment here, and it definitely looks like a $3 mark. It's got $2 here, we've got $4 here, so somewhere in between would be $3. So the coordinates of the y-intercept would be 1970, 3. I'm in favor of that. I'm comfortable leaving it that way. There is a possibility that the teacher might want us to represent 1970 as year 0, since it's the literal beginning of our analysis. There is that chance, but I'm going to assume that the teacher does not insist upon calling 1970 year 0. We will instead simply call it 1970. All right, so 1970, 3. I'm comfortable with that as far as the x and y coordinates of the y-intercept. Now, as far as what it means, I would agree with this phrasing here. Costed is not a word, but that's okay. In 1970, a Bugs Bunny shirt, we'll say cost $3. All right, that's true. In 1970, how much was the shirt? $3, clearly. All right, that's what it means. Moving on to this one. What is the rate of change, also known as slope, and explain what it means. Slope, usually denoted by an m, is always going to be the change in y all over the change in x. Y definitely, the change in y means, how much is something going up or down. The change in x definitely means how much is something going left or right. Let's see. Right. Okay, well, first of all, the handwriting is not the best, so I'm going to sort of go off to the side. Not that my handwriting is that much better, but I'll try to make it a little bit better. So once again, we want to know the change, the rate of change over here. And I would agree. The rate of change, sometimes denoted by m, is the change in values of y all over the change in values of x. Hopefully you at home recognize that this triangle means the change of values. I believe it's delta, if I'm not mistaken. So it's the change of values in y and the change of values in x. And let's sort of investigate the change in values of y first. And before we do that, what I would like to do is go off to the side and just write down 2 points that are definitely on this line. We're going to stick with this point and this point, and we'll start with this one. We already wrote the coordinates of this. It is 1970, 3. And the coordinates of this point right here are going to be 1990, and that looks to me to be 5. Let's see. Yes, it looks like this y value is 5, so we'll make a note of that right now. We've got 5 over here. And let's also keep in mind that these are both, x and y terms. So when we're dealing with the change in y, we want to deal with the change in y's here. And the change in y's would be 5 minus 3, or we could say the distance between 5 and 3. And the best way to figure out what the distance is between 5 and 3 is to subtract 3 from 5. So we're going to do that right now. We've got 5 minus 3, and that's going to be all over the change in x. Now, the change in x values would be the distance between 1970 and 1990. Now, a lot of us can do that in our head. We know that it's 20 years, but let's sort of map it out nonetheless in an official way by saying 1990 minus 1970 down here, and that would definitely result in 2 over 20. So that gets us really close to our final answer. You know, this is zeroing, and we're honing in on what the rate of change is, also known as the slope. It's going to be 2 over 20, but this is not fully reduced. So we're going to want to reduce this. Now, I'm going to assume that the people watching this video know how to reduce fractions. This turns into a 1. This turns into a 10. So at the end of the day, what we have as our final answer is 1 over 10, and I will circle that or put a box around that. So that's the rate of change. Unfortunately, the teacher wants more information. We want to know, what does it mean? Well, what this means is, since we are dealing with, let's see, money up top and years down below, we know that every 10 years gone by, the cost of the shirt rises $1. So I'll even put the dollar sign over here. Money up top, years below, right? So with every 10 years passing by, the shirt increases. The cost of the shirt increases by $1. That's what it means. Okay? Moving on, let's take a look at this next part. Write the function rule for the graph. Okay, I'm just going to focus solely on this. I'm not going to bother with this just yet. I'm going to focus solely on this. Write the function rule. In other words, what is an equation that would work well to describe the behavior of this line? What would be a good linear slope, or I should say linear equation? And I see this y equals mx plus b thing over here, which makes me think that the teacher definitely wants it in slope-intercept form. So let's analyze this. I'm looking down here, and this handwriting is pretty good, so I think it's worth analyzing this. If we're going to do the function rule, it looks like the teacher is once again insisting upon slope-intercept form, which takes the form of y equals mx plus b. Hopefully everyone at home recognizes that this is the y-intercept. I'll call it y-int for short. And this right here is the slope. All right. Now the good news is from the last problem, we actually have the slope. The slope ended up being 1 over 10. And in fact, I'll write that nicely here. 1 over 10. That's the slope. And the slope would therefore go in this m position, glued to this x. It looks like my student did that correctly. We have 1/10 times x right here. And then we have the y-intercept. Now, before we had found the coordinates of the y-intercept, right? Because that's literally what the teacher asked for. But the y-intercept itself is always just this number, 3. It's always going to be, we could say, the y-coordinate of the coordinates of the y-intercept. That's kind of confusing, but just know, if the teacher asks for the coordinates of the y-intercept, you're going to want to write an xy coordinate thing. If the teacher just wants the y-intercept, it's going to just be this number. All right, so hopefully that makes sense. A little confusing. But looks like my student recognized it because the y-intercept often denoted by a b, because the b is right here. B equals 3, right? Because that's 3. So b equals 3, and my student correctly put the 3 where it belongs. So I am a huge fan of what happened here with what my student wrote. Okay, moving on. Using the function rule, determine the cost of... I see a Tweety Bird that got crossed out. Bugs Bunny shirt in 2030. Approximate to the closest dollar amount if needed. Okay, yeah, so this is sort of the purpose of even figuring out what the function rule is, because it enables you to find out, like, all right, well, we know how much the shirt cost in 1990. We might even know what the shirt cost in 2010. But what's the shirt going to cost in 2030? Ha 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 ha. Now let's say you don't want to draw a huge graph. Well, that's the purpose of the function rule, is to help you avoid drawing a huge graph. And that's what we're going to do right now. So I'll write the function rule over here. We already figured out that it is y equals 110x plus 3. And let's take a look. We want to know what's it going to be in 2030. Okay, so if we want to know what the cost is going to be in 2030, I'm recognizing right now that actually it will be helpful when you're busting out the function rule and approximating the closest dollar amount in 2030. At this point, it will be necessary for us to see 1970 as year 0. So that's what we're going to do. We're going to see 1970 as year 0. And to avoid a complicated explanation, I'm just going to say, if you're going to use a function rule in a problem like this that features time and a starting point of analysis in 1970 or some other time, if you're going to use a function rule to predict future dollar amounts at a certain time in the future, that at that point you might want to consider the starting year as year 0. Okay, so that's a good piece of information to remember if you're going to be dealing with a function rule. And I could sort of explain why that is, but I would invite everyone watching and my student to just sort of take my word for it for now, in the interest of saving time. Sort of proving this has to do with setting the x coordinate, or the x value, substituting in 0 for x and y equals 1/10 x plus 3, recognizing that that would give us a y value of 3. But I'm not going to get into any of that. Let's just call the starting year 0. And if the starting year is year 0, that would make 1990, well, what? That would be 20 years from the starting point. So from that point of view, we could call this x value 20, and we could call this x value right here 40, which basically means 40 years from the starting point. All right. So once again, just sort of taking my word for it. So we have that. And if we want to know, use the function rule, determine the cost of a shirt in 2030, well, we need to ask ourselves, how many years is 2030 from our starting point? Well, 1970 to 2000 is all I'd write. Instead of x, I would write 1/10 times 60 plus 3 and work it out from there. So this is a 10, by the way. 1/10 times 60. That's the same thing as saying 1/10 of 60. 1/10 of 60 is the same thing as saying 60 divided by 10, which is 6. So we have y equals 6 plus 3, which is 9. So in other words, in 2030, this shirt is totally going to be $9, assuming everything stays the same. All right, so that's how to do that one. All right, moving on. 5. We've got parallel lines. We've got this big line cutting through that is called a transversal. Okay, list all the sets of corresponding angles. So my student has a beautiful sort of summary reference guide of, you know, what the names are for these angle relationships. So I would invite my student to definitely memorize this stuff for sure for future tests. It's kind of a pain in the butt memorizing stuff, but you do have to do that often in math, unfortunately. So anyway, list all the sets of corresponding angles. So corresponding angles are angles like 6 and 2. Notice how 6 and 2, they're the same size. Even to the naked eye, they look like they are the same size. So 6 and 2, that would be a pair of corresponding angles. Another pair of corresponding angles would be 5 and 1. We can also say 8 and 4 are corresponding angles, and we could also say that 7 and 3 are corresponding angles. So we could say, let's just analyze 6 and 2. It's corresponding because it's on the same side as the transversal, and they are of equal angle measure. All right, where one is on the interior of the parallel lines, and the other one is on the exterior of the parallel lines. So that's corresponding. Let's see. I'm not exactly sure what my student wrote here. This might be something that I'm just sort of unfamiliar with regards to how this is listed. I think what I would have done, and hopefully this doesn't fly in the face of what my student's teacher wants him to do, but I think what I would have done here is I would have written, I don't know, something like, 6 and 2, and maybe put brackets around it, because often sets are denoted with brackets. Again, not sure if that's exactly what the teacher wants, but the teacher would look at it and see that it's not incorrect necessarily. So these are the sets of corresponding angles right here. And I'm comfortable with that. Hopefully the teacher would hypothetically be comfortable with that as well. Moving on. B. Angle blank is vertical to angle 7. Well, that's definitely angle 6 for sure. And the reason is because here's angle 7. Vertical angles are the angles that are like across from each other, and they also happen to be of equal measure always. So we have 7 across the angle from 6. That's why they are vertical angles. It's important for students to recognize that don't get thrown off by the word vertical. We're so used to vertical meaning up and down, but when it comes to vertical angles, they won't always look like they're going up and down. Clearly with 7 and 6, you're kind of going off to the side like that, so it doesn't really look vertical, so that could be somewhat deceiving. Let's see, list all sets of angles that are linear pairs. So once again, I'm seeing similar writing as with part A, so maybe this is something akin to what the teacher is looking for, but nonetheless, I'm going to use my sort of bracket notation for that part as well. So let's look at that. Okay, looking at problem C. So first of all, what is a linear pair? A linear pair would be two angles that are first of all right next to each other, so they're adjacent, and they form a straight line. Once you put them next to each other, they add up to 180 degrees. So clearly you can see 1 and 2 would be a linear pair. So I'll write that right now. 1 and 2 is a linear pair. We could see that 2 and 4 is a linear pair. We can see that 4 and 3 is a linear pair, and we could also see that 3 and 1 is a linear pair. And similarly on the bottom section here, we've got a whole bunch of linear pairs as well. We've got 5 and 6, we've got 6 and 8, we've got 8 and 7, and we've got 7 and 5. Good times. So that's the answer to that problem. Angles 5 and 4 are a pair of blank angles. So 5 and 4 are a pair of alternate interior. So this is correct. Now, why are they alternate interior? Okay. Well, first of all, we have a nice reference guide over here. But 5 and 4. So what do we mean by the word alternate? You see this little word alt? That means alternate. What do we mean by alternate? Well, here's 5 and 4. It's alternate if the angles are on alternate sides of the transversal. All right? So the first word, alternate, is referring to the transversal. The relationship of the angles around the transversal. Right? So that's important to recognize. The next part of the answer is the word interior. And what that refers to is the fact that you've got 5 and 4, and they are both inside the parallel lines. Right? They're inside of the train tracks. That's what is being referred to by this second word, right? So that's important to keep in mind, that when you're calling something alternate interior or same side interior or alternate exterior, the first word has to do with the relationship of the angles around the transversal, and the second word has to do with the relationship of the angles with regards to the parallel lines. Are they on the inside of the parallel lines, or are they on the outside of the parallel lines? Of course, if they are on the inside of the parallel lines, the angles will be interior. And if they are on the outside of the parallel lines, the angles will be exterior. It so happens that 5 and 4 are on the inside of the parallel lines, which means that they're interior. So let's see, looking at the final question, angles 4 and 6 are a pair of blank angles. So 4 and 6, right. So yes, 4 and 6 are consecutive. There is a listing of consecutive down here with 1 and 2. So this could just be a matter of remembering that that's what consecutive means. Now, the word consecutive in general means like the one that's after the other naturally. The one that's naturally after the other one. So we could say there's 6, and then right after 6 is 4, if we're going to be moving in this direction, all right? I think other math teachers might emphasize whether or not 4 and 6 are not only consecutive, but are they consecutive interior or are they consecutive exterior? For example, we could say that 8 and 2 are consecutive exterior. All right. I've also heard something like 6 and 4 as being same side interior. So these are all words to describe the same phenomenon. It looks like my student's teacher wants to call these consecutive numbers, consecutive angles, and this is a beautiful reference guide for that information. Moving on. Okay. So here we have a diagram. I'm going to actually redraw this scenario over here because the writing kind of throws me off a little bit. But that's E, that's B, that's C, that is D, and we have A down here. And anything else? Let's see. Okay, so they say angle A is 5x minus 15. So I'm going to actually write that here. I'm going to write 5x minus 15 right here. I think it's always a good idea to label stuff. And let's see, angle B is 3x plus 45. So I'm actually going to write that right here, 3x plus 45. Now right away, the way that my mind works with this is I just labeled angle A, I just labeled angle B, and we could also see clearly that A and B are vertical angles, so I can already see that 5x minus 15 is going to definitely equal 3x plus 45, no question. Let's see. Using the expressions for both angles A and B, determine the value of x exactly. So we're going to take advantage of the fact that we know that A and B are vertical angles and write an equation that follows suit from there. And that would be 5x minus 15 equals 3x plus 45. I'm going to subtract 3x from both sides right now. That would give me 2x minus 15 equals 45. I'm now going to add 15 to both sides, and that would give me 2x equals 60. And then dividing both sides by 2 would give me x equals 30. So that's x. X is 30. No question about that. All right. The next thing asks, now knowing x, determine the measure of angle E. Well, that would be this angle right here, this angle right here. Okay, so we know what x is. I mean, x is 30. If x is 30, then that means we could just replace this x with 30 and sort of figure out what angle A is. That's not a bad idea. So I will actually erase this right there, and we're going to replace it with 30. 30. And as a result of that, it's going to be 5 times 30, which is 150, minus 15, which would be 135. So I'm going to actually erase the whole thing right here and replace it with 135 right now. Which, for the record, by the way, makes this 135 also. All right, but anyway, this is 135. We want to know, what is angle E? Well, clearly we can see that angle A and angle E are a linear pair, meaning that they are next to each other, and they form a straight line, and they add up to 180. So 135 plus angle E equals 180, and it is that insight that enables you to solve this problem. So I'm going to call angle E y. Okay. We're just going to assign the variable y to it, because now we can write the equation. It's 135, which is angle A, plus y, which is angle E. We'll use the angle symbol. And that's going to equal 180, right? So let's see. 135 plus what equals 180? We could go through the motions and solve for y by subtracting 135 from both sides, but we could also realize that, 135 plus what will give us 180? Well, that would be 45. 135 plus 45 would give us 180, so I'm just going to write that. 45. That is what angle E equals. Y equals 45. So actually, I'll just erase that, and we're going to write 45 in there. Done. Okay, what is angle D? How did you determine its measure? So angle D is over here. Let's see. Well, before I even get to that, to be honest, you know what I'm going to do? This is annoying to me, this x here. I mean, we already know what x is. I mean, x is 30, right? And we could always substitute 30 in there, and we would realize that this is equal to 135. Or we could just recognize that if angle A is equal to 135, then that means that angle B is equal to 135. So I'm actually going to write 135 here because I don't want to deal with that annoying expression right there. So we're going to write 135 right there. And now we're asking, what is angle D? How did you determine its measure? Well, angle D, I can already tell is 135. And the reason is because this angle right here is a corresponding angle with this angle right here. So on the last slide, we went over what corresponding angles are. They are most definitely these angles right there. All right. So, or you could think of it as, let's see, we could also think of it as these angles right here. Okay, one way or the other, angles that are on the same side of the transversal, but they equal each other. They are the same size, where one is on the exterior and one is on the interior of the parallel lines. Well, that's what we have here. We have this on the exterior of the parallel lines. We have this on the interior of the parallel lines, and they are on the same side as the transversal. So guess what? No algebra even required. Not really. this is 135, just simply based off of the fact that this is 135. Done. Okay, using the rules of exponents, simplify each expression. Be sure your answers involve any positive exponents. Let's see. Yeah, so looking at A, I'm just going to rewrite that over here. Negative 2x to the 6 times 5x to the 4th. Now, you don't always have to write this, but you might actually want to at least think of the numbers being next to each other and the terms, the variables with the exponents being next to each other as well. And we're allowed to kind of do this because multiplication is commutative, meaning you can shuffle these around and multiply this stuff in any order that you want. In my opinion, thinking of it this way is very easy on the brain because we could just do this times this and this times this. Now, negative 2 times 5 is, of course, negative 10. And what you want to do here when you have two of the same variable with the same or different exponents and you're multiplying them together, you're going to keep the base, which is x, and you're going to add the exponents. That is something that you might just want to memorize. And this becomes, therefore, negative 10 to the 10 times x to the 10th power. And that's all there is to that one. Okay, looking at the next one, which would be B, we have negative 2 times x to the 3rd raised to the 6th power. Okay, so it looks like my student was kind of on the right track here. It's almost as though you're distributing this 6 to this guy and to this guy. All right, so it's helpful to think of this as two numbers. All right, you have a negative 2 times an x to the 3rd. And when that whole product is being raised to a power, you could think of it as it's sort of like distributing the exponent to both of these. So I'm a big fan of using parentheses. As any of you have seen my other videos, I talk about that a lot. So it's going to be negative 2 raised to the 6th power and x to the 3rd raised to the 6th power. Now let's analyze what's going on here. Now, negative 2 raised to the 6th power, that is something that you could plug into your calculator for sure. Now, first of all, anytime you raise a negative number to an even power, it's going to become a positive number. So we know that whatever this becomes, it's going to become a positive number. Once again, if you have a negative number raised to an even power, it's going to become a positive number. So it's going to be positive something, and that would be positive 2 to the 6th. Well, let's see, 2 to the 3rd is 8, times another 2 to the 3rd is 8, so this is going to become positive 64. Now let's analyze this situation. Well, anytime you have a variable raised to a power and then it's raised to another power, well, you multiply these two. All right, you multiply these two. Now I want to contrast this between another scenario soon, but let's just write down what the answer is. This is going to become x to the 18th. All right, now here's the big takeaway here. What did we just do? And by the way, we just finished that. But what's the common mistake that a lot of students make? What they do is they'll be like x to the 3rd raised to the 6th, and they'll make the mistake of treating this as though it is the same as this. All right? We want to be clear, these are not the same. All right? This scenario is not the same as this scenario here. Okay? This scenario here is completely different. So in this case, we want to keep the base and add the exponents. In this case, we want to keep the base and multiply the exponents. Okay? So these are completely different situations. So take that in, pause the video, take a good hard look at this rule, and notice how these are completely different scenarios. All right, moving on, we've got this right here. I'm just going to copy it down. negative 2x to the 5th raised to the 3rd power. I'm already seeing that we're going to have to do something similar to what we did last time. Okay, well, if we're going to do PEMDAS, we want to take care of the parentheses first. Ask ourselves, are these, the content within these parentheses, are they as simplified as could be? If so, leave it alone. If not, then combine things and simplify things. Well, it looks like negative 2x to the 5th power is as simplified as it could be. So in PEMDAS, we then move to exponents, which means apply this exponent to these guys first, right? So we're going to apply the exponent. It's going to go here and it's going to go here. Once again, I'm going to treat this as a number and this as its own number. So we'll actually write that. It's negative 2 to the 3rd times x to the 5th to the 3rd. And then we still have multiplying that times negative 2x to the 4th. All right. So let's analyze this scenario. Negative 2 to the 3rd power. Now, anytime you have a negative number raised to an odd power, that is going to give you a negative number. So it's going to be negative something. So then the question is, what's 2 to the 3rd power? Well, that would be 8. So this ends up becoming negative 8. Looking over here, we have x to the 5th raised to the 3rd power. In this situation, you're going to want to keep the base and multiply the exponent. So this therefore becomes x to the 15th times this negative 2x to the 4th. Once again, like I had sort of done before, you might want to think about this as, well, you might want to think about it as 4 different numbers being multiplied together. It's helpful to separate things out in your mind when things get a little confusing looking. What's really going on is a string of 4 numbers being multiplied together. We got negative 8 times x to the 15th times negative 2 times x to the 4th. Since multiplication is commutative, that means we could write this in any order we want. And I'm going to suggest multiplying negative 8 times negative 2 and having them next to each other. And then we're going to have that next to x to the 15th times x to the 4th. And let's try this first. We've got negative 8 times negative 2. Well, that would definitely be a positive 16. And then over here, we've got x to the 15th times x to the 4th. Well, you keep the base, and in this case, you add the exponents. So that would be x to the 19th, and that is the answer to that. And it looks like my student did that correctly as well. So that is how you do that one. And finally, looking at the last one, which is most definitely the most complicated looking one for sure. We've got negative 2x to the 5th raised to the 3rd power times negative 2x to the 0 power times y raised to the negative 8 times negative 3x to the 5th times y to the 3rd. Now this is most definitely an intimidating looking problem, but it's not that bad as long as you take things one step at a time and relying on PEMDAS. Now PEMDAS, once again, would suggest that you apply any exponents before you do any sort of multiplication. We have a great opportunity to apply the exponent here, as we've sort of covered in the last couple problems. We're going to apply the exponent of 3 to that number and to this number. So this number is negative 2. This number is x to the 5th. So right underneath, I'm just going to write, negative 2 raised to the 3rd times x to the 5th raised to the 3rd. And I'm going to say let's just leave that there for now. On the next line, we could go further with it, but let's actually keep writing across and see if there's any opportunities to do anything with these guys. So looking here, number 1, anything raised to the 0 power is just 1. So in a sense, we could just sort of ignore this one. Okay, and what we're left with, therefore, is negative 2 times y to the negative 8. All right, I'm just going to write that for now. In fact, I'm going to separate all of these numbers to make it clear that it's just a string of numbers that is being multiplied together. And over here we have negative 3 times x to the 5th times y to the 3rd. Now, I'm acknowledging that this might be an uncommon approach. It's not every math teacher that talks about separating things in parentheses, but I find that this is really helpful for me because it actually makes it less intimidating. To me, this looks like a bunch of gobbledygook whereas this looks like neatly compartmentalized numbers. And it's just a reminder to my conscious and unconscious mind that there's nothing really intimidating happening. It's just a string of numbers being multiplied together, and then on every subsequent line, we can simplify it one step at a time, no rush. So anyway, negative 2 raised to the third power, well, that is a negative number raised to an odd power. That ends up becoming negative 8. Let's keep it in parentheses. Let's see, we've got x to the 5th raised to the third power. That's going to be a matter of keeping the base, multiplying the exponents, so that's that. Negative 2 we'll just leave alone. Okay, so we've got y to the negative 8th. Well, that is definitely equal to... Yeah, we're going to put it like this. It's equal to 1 over y to the 8th. So basically, anytime you have a negative exponent, you could take the number, shove it into the denominator, and change the sign of the exponent. All right? So in other words, you know, if I had like x to the 10th, well, that would equal, you know what? That would equal 1 over x to the, drum roll, positive 10th. Okay? That's how that one works. All right, so that's what you could do with negative exponents when they're up here. We're going to leave that negative 3 by itself. We're going to worry about that later, and we'll leave these alone as well. And the reason I'm leaving these alone is because on the next line, I want to just group everything. I want to group the like terms near the like terms. So negative 8 is a regular old number. We're going to put that next to negative 2, and we're going to put that next to negative 3, because these are just the numbers, right? So we've got negative 8, negative 2, and negative 3 all next to each other. Now we've got x to the 15th and x to the 5th, and we could do that in our head, but, you know, I'm a fan of doing these intermediate steps to avoid careless mistakes, so we're just going to write that. And now we're going to deal with the y numbers right here. Now y to the third times 1 over y to the 8th, it's helpful to remember that y to the third secretly has a 1 underneath it. So what you have here is a fraction times another fraction. And what do you do when you multiply a fraction times another fraction? Well, you just multiply the numerator straight across, and you multiply the denominator straight across. So that would result in y to the third all over y to the 8th. All right, let's see if we can make some headway with this. Let's see what happens when we multiply these numbers. Negative 8 times negative 2 is positive 16, times a negative 3 is a negative 48. That's what that is. Keep it in parentheses for now. We have x to the 15th times x to the 5th. In that case, you would keep the base, add the exponents. And let's see, over here, y to the third over y to the 8th. Let's sort of analyze what's going on over here. So y to the third over y to the 8th. Well, what is y to the third? Y to the third is really 3 y's being multiplied together. Y to the 8th is really 8 y's being multiplied together, right? That's what this is, right? And you could do cancellations, right? This is one way of thinking about it, where this cancels with that, this cancels with that, this cancels with that, and that leaves these 5 y's on the bottom and an invisible 1 up top. So what we have, therefore, is 1 over y to the 5th. Now, there are multiple ways of doing this thing. There are multiple ways of handling negative exponents, but this is one of numerous ways that we could tackle this, all right? Hopefully it's not straying too far from what the teacher is looking for. Now, it is such that we might want to sort of rewrite the final answer in a more compact way, and that would be negative 48 times x to the 20th all over y to the 5th. That's a nice compact way of writing the final answer. And you might ask, well, why is that? Why do we have the y to the 5th shoved obnoxiously underneath these numbers? Well, that is once again because secretly there's a denominator of 1 under that. Secretly there's a denominator of 1 under that. So this is really, you could think of it as 3 fractions being multiplied together. And what do you do when you have 3 fractions multiplied together, or any fractions multiplied together? You multiply the numerator straight across. Well, that's what we did. 1 times x to the 20th times negative 48 is negative 48x to the 20th. And then you also multiply the denominators across. You have y to the 5th times 1 times 1. Well, that would just be y to the 5th. That's why we end up with this nice, neat number here that is very compact. Moving on. Okay, so what we have here is a transformation. I kind of redid this part to make it nicer looking. The picture was kind of wrong and weird looking. So let's see what's going on here. Translate the figure 7 units up and 1 unit to the right. Well, here's the figure, right? Translations upwards and to the right and all that, they're fairly easy, fairly intuitive. It basically means take all the points of the shape, and you could use the vertex as these like markers in a way to sort of figure out how many units up, how many units to the right you're going. You'll see what I mean by that in a second. But for now, basically we're just going to take this whole shape and bring it up 7 units and to the right 7 units. Now, this is where it like really helps to have a pencil, because what you could do if you had like a thin pencil is just maybe choose one reference point and work with that. So for example, let's focus only on the top left corner. If we're going to bring it up 7 units, then it's going to go 1, 2, 3, 4, 5, 6, 7. And now the top corner is right here. You know what I mean? Now, could I do that with all of these other points and bring it up? Well, maybe, but I'm just going to focus only on this one reference point because I have faith in my ability to draw the entire rectangle based off of this one single reference point. Now, we're not done. We brought this 7 units up. They also want us to bring it 1 unit to the right, so the reference point ends up right here. Now, once again, this is the top left corner, and we could also take note of the dimensions. This is a rectangle that is 4 units high and 2 units wide, so we're just going to draw a rectangle that is 4 units high and 2 units wide right there. So there we are. So we at least accomplished the first part, right? Which says bring this thing up 7 units up and 1 unit to the right. Now it's saying reflect the figure about the y-axis. Now there's multiple ways of going about that. First of all, what is the y-axis? Let's get clear on that. The y-axis is most definitely this axis right here, okay? So that's the y-axis. We're going to reflect this figure across the y-axis. Now there's, again, multiple ways of doing this that take into account maybe, you know, the different points on the corners. However, this is something that's sort of similar to this. We can eyeball this, in my opinion. All right. Now the way to think about this is you want to think about this y-axis as a mirror, right? And we want to have a perfect reflection over here. Right? Now, what I would do is think about, okay, how far away from the surface of the mirror is this box? Well, we could once again kind of use this as our reference point right there. How many units away from the mirror is that reference point? And that would be 4 units. So you know what we're going to do? We're going to go 4 units over here, and we're going to draw a point there. So that's actually 1, 2, 3, 4. It's going to be right here. All right. I'm going to clean that up a little bit, actually. Let's zoom in. Let's make sure that we're being really precise. So it's going to be 1, 2, 3, and 4. It's going to be right there. So that's where that reference point is now. And I'm just going to erase this right here. And, you know, I have faith in our ability to draw the box from there, knowing full well that we're treating the y-axis like a mirror. And if this is the reference guide, this is the corner that's closest to the mirror. So in the reflection, this should be the corner that's closest to the mirror. All right, so then we're going to draw a 2x4 box accordingly. All right, so we have satisfied that part also. Let's look at the next part. Rotate 90 degrees counterclockwise. Okay, so here's where it gets a little tricky. I'm going to write down, first of all, let's get clear. Clockwise is this way, right? I think most people realize that. It's to rotate this way. And counterclockwise is to rotate this way. Now, we are focusing only on counterclockwise, so in the interest of saving time, I'm going to only concern myself with counterclockwise rotations. Now, when you're dealing with counterclockwise rotations, it's helpful to think of actually numerous reference points, but here's what you're going to do with each reference point. Now, let's say this is an original reference point. When you rotate counterclockwise, you're going to turn what used to be x comma y into the following. It's going to turn into negative y comma x. Now, if that's not clear, it's going to be right now. So what do I mean by original reference point? Well, we've already worked with a reference point. We had this reference point. We used that to bring it up here and then over. Then we used this reference point to figure out what the reflection is. And then we ended up here. But now, of course, we're dealing with rotation. This is where it might be helpful to get 4 reference points. So let's get clear on the 4 reference points right here. What we have right here is negative 6 comma 5. We have negative 4 comma 5. We have negative 6 comma 1, even though it doesn't look like it. We have negative 4 comma 1. All right, so now we have these 4 reference points, and what I would advise is setting up the following chart. Okay, so there's 4 rows to this, which will be the home for the 4 reference points. The only reason I'm drawing those arrows at an angle is to avoid the logo. Otherwise, they would go straight across. So the reference points, once again, are negative 6 comma 5, negative 4 comma 5. We've got negative 6 comma 1, and we've got negative 4 comma 1. And according to this schema right here, we're going to turn this into that. So we're going to take whatever y is and make it negative and put it right here. So let's do that right now. So y is 5, so therefore negative y would be negative 5. And then we still have our negative 6 hanging out. Y in this case is also 5, so this will be a negative 5. And then that negative 4 is just hanging out. This would be negative 1 for the same reason. And this would be a 1, a negative 1, negative 4. So, you know, counterclockwise rotation, you take the x, put it over here, and you change the sign of y and put it over here. That's literally what we did with each of these. 5 became negative 5, negative 6 stayed itself, but went over here. This 5 became negative 5, negative 4 stayed itself, but went over here, and so on. That's the rule for counterclockwise rotations, and these are our new points. These are our new points that we're going to use to plot the next rectangle. So we have negative 5, negative 6, negative 5, negative 4, negative 1, negative 6, negative 1, negative 4. So negative 5, negative 6. Let's look at that. negative 5, negative 6 is going to be right here. We'll use blue. Negative 5, negative 4 is going to be right here. Negative 1, negative 6 is going to be right here. And we could already kind of see that the next one's going to be right there. So this is where we are right now. All right. So a systematic approach when it comes to rotations is the best way to avoid careless mistakes. Now, dilate with a scale factor of 1/2. What the heck does that mean? Okay, so basically what that means is if you've got, usually when they say dilate, they mean dilate it towards the origin. So it's like dilating this towards the origin, which means either scale it up, make it bigger and further away from the origin, or shrink it down and bring it close to the origin by a scale factor. Now, let's get clear on what we mean or how we can navigate the scale factor. When it comes to a scale factor and dilation and all that stuff, I think it's very helpful to take a similar approach as to the approach that we just did. And what I mean by that is we're going to list our current 4 reference points again. All right. And we're going to turn them into a new batch of reference points. And these 4 points are the corners, of course, of the rectangle. Now, here's where we are right now. And we're going to write the coordinates. So we've got negative 5, comma 4. That's one of them. Negative 4, I should say. We've got negative 5, comma negative 6. We've got negative 1, comma negative 4. And negative 1, comma negative 6. Now, when we apply a scale factor of 1/2, what that really means is you're going to multiply 1/2 times, or the scale factor times whatever x and y is. All right. Now, make no mistake, if the scale factor was not 1/2, let's say the scale factor was 10, well, this would be 10 times x, 10 times y. So whatever the scale factor is goes here. Okay. Now, we're going to do these calculations in our head with regards to these coordinates. So let's see. Negative 5 times 1/2 is negative 5 over 2. Negative 4 times 1/2 is negative 2. Once again, negative 5 over 2. Negative 6 times 1/2 is negative 3. Negative 1 times 1/2 is negative 1/2. And negative 4 times 1/2 is negative 2. Negative 1 times 1/2 is negative 1/2. And negative 6 times 1/2 is negative 3. So these right here are our new reference points. And by the way, that is the final shape as well. Now let's get very clear. In decimal land, negative 5 over 2 is really 2.5. And in decimal land, negative 1/2 is really 0.5. So we're going to plot this now. Let's take a look. We'll do it in red. Negative 2.5, negative 5 over 2, also known as negative 2.5, comma negative 2 would be right here. Let's see, and negative 2.5, comma negative 3 would be right here. And we also have negative 1/2, comma negative 2, which would be right there, actually. It's kind of a weird graph. And then we have negative 1/2, comma negative 3, which is going to be right there. So that is our final rectangle. And the final thing that they ask us to do is to shade the dilated figure and list the new prime coordinates for all 4 points. Well, we kind of did that, you know. We kind of listed the prime coordinates. Here are the prime coordinates, and we shaded the final thing. The teacher might want you to maybe zoom in and label the coordinates, so we could do that. Let's get really close. And I like to just do things systematically. I know I'm going to be doing this either way, so I just do it. That's negative 2.5, 2, negative 2. This one here is negative 2.5, negative 3. This one is negative 0.5, negative 3, and this is negative 0.5, negative 2. It's kind of ugly looking. My handwriting's not the best, but you get the idea. That might be a nice way of kissing the teacher's butt, is by actually labeling it on the graph. So that is how to do that one, and that is the final problem.